I'm actually extremely excited for this one. You probably aren't because you clicked on this video because it can be a really daunting topic and pretty unclear what's going on. But we're talking about the mean subspaces, subspaces of Pn and Mn. So polynomial and matrix subspaces. Now these subspaces have to obey the exact same rules as our subspaces of Rn, so we have to be closed under vector addition, scalar multiplication, and we have to include the zero vector. So for any two elements of our set, if we add them together, we should get another element of our set, and if we scale any element, we should get another element of our set. And being able to scale by the factor 0 is the reason why we need to include the zero element. Okay, so let's just get going. Let M33 be the real vector space of all 3 by 3 real matrices. Which of the following sets is or are subspaces of M33? Okay, so really the first question we should ask ourselves with all these three is if we take two matrices that are either orthogonal, symmetric, and singular, and add them together, do we get a product, or what do we get from that? Is that still orthogonal, symmetric, or singular? So let's go backwards. Let's go to number 3. Let's find two singular matrices. I like what about 1, 1, negative 1, 1? That is not singular. Wait, I gotta fix it. There we go. And then let's add that to, I don't know, 1, 5, negative 1. No, let's make that a 6 and make this a 2 and a 3. There we go. So these both have a determinant of 0, so they're singular. When we add them together, we get 3, 0, 2, 3, 0, 2, and 7. What's this determinant? Well, it's non-zero. So clearly, the set of all real singular matrices in 3 by 3 is not closed under vector addition. What about symmetric matrices? Actually, let's come back to that. Let's go to number 1, the set of all orthogonal real matrices. So let's pick two. Oh, I just realized I was dealing in 2 by 2. Yeah, that example I just used was for 2 by 2 singular matrices, but here's a little secret. These properties will apply no matter what dimension we're dealing with here. So it's a little bit of a cheat, but we're fine making these little examples for ourselves. So what about two orthogonal matrices? What about 1, negative 1, 1, negative 1, 1, 1, and then let's add that to, we can do the same kind of thing, 6, negative 1, 2, 3. So the dot product of these two columns gives us 0, and the dot product of these two columns gives us 0. When we add them together, what do we get? 7, 3, 4, negative 2. So we have negative 14 plus 12, that is not 0. So this will generalize to the 3 by 3 case, and it turns out 3 by 3 symmetric matrices are also not closed under vector addition. So we know our answer. It's 1 only, orthogonal. I'm sorry, we just checked orthogonal. Sorry about that. So yeah, we know our answer. It's 2 only, but why? So if we take an arbitrary, this time I'll go in 3 by 3, symmetric matrix, 1, 2, 3, 4, 4, 5, 5, 6, 6, and just think about what happens if I try to scale any of these values here. Well, if we scale the entire matrix by something, it's still going to be symmetric. Let's scale it by a factor of 2. We'll get 2, 4, 6, 8, 8, 10, 10, 12, 12. So because everything across the main diagonal is getting scaled equally, we're left with something. We're left with something that is also symmetric. Now, if we add a symmetric matrix to another symmetric matrix, the same kind of thing will be happening. We'll be adding the same thing along 2, 7, 3, 3, 7, 2. Well, we're adding the same thing to opposing elements along the main diagonal, so we get 2, 3, 4, 6, 6, 10, nope, that's not 10, that's 12, 12, and 9, 9. So no matter what we do, we're always adding the same thing across the main diagonal. And then finally, our final reason why this is a subspace of M33, I don't really like how they're writing this here, but whatever, is because the zero matrix is symmetric, right? Because if we draw out the 3 by 3 zero matrix and we take its transpose, or we just take a look at it, but we take its transpose, we're just getting the zero matrix. So there we go, that's great. And in fact, the zero matrix is also orthogonal and singular, so it satisfies those. But you know, our other ones are not closed under vector addition, at least. We didn't even check scalar multiplication. So there we go, we get D as our correct answer. 14, let M 3 by 3 be the space of 3 by 3 matrices. Let H be the subspace of M 3 by 3, consisting of all matrices A, given there, such that A times 1, negative 2, 0 is equal to 1, 1, 1. This question I figured out today, or I knew what the answer was before, but I didn't like my own explanation for it, and now I really like my explanation for it. So, with all of these questions, and in fact, the next two as well, we're counting the dimension of these subspaces. And really, instead of trying to think of it geometrically, let's think of it in terms of degrees of freedom. So, if we have some variable that we can, move around completely freely in our system, then that is a degree of freedom that our system has. So let's solve this a little bit, and then I'll tell you the other half of what's going on. So if we solve A times 1, negative 2, 0 is equal to 0, 0, 0, we see that A minus 2B, D minus 2E, and G minus 2H must be equal to 0, 0, 0. So we have these three individual equations that are really defining our subspace here, but we have to look a little bit behind the scenes too. So we have these three variables, C, F, and I, that are not included in here. Well, what does that mean? They're free variables, so we can vary them all we want. So C can go between negative infinity and infinity, and so can F and I, without changing anything here. So because they're purely free variables, meaning that they're a completely free degree of freedom, we can change them without having to change anything else in our system. Each one of them contributes one degree of freedom, or one dimension to our subspace. So right now our running total is 3. But what do we get? What do we get from these three equations that we have here? Well, you might think, okay, well we have six variables left here, so we must have 6 degrees of freedom. Well, there are two explanations that you can use to count up the rest of the degrees of freedom that we have. You can go geometric and say, well, each of these we can express as a line, so A equals 2B. For every unit A, we have to move 2B in order for this to still be equal to 0. So really, we don't have full control on the A-axis, and we don't have full control on the B-axis. We only get one dimension of control. A line is one-dimensional. If this was A plus B plus C equals 0, you can think of that geometrically as an X plus Y plus Z is equal to 0, just as a plane passing through the origin. A plane is two-dimensional. This thing has 2 degrees of freedom. Additionally, you could really just think about this as A and B can do whatever they want. They can change all over the place as long as C accounts for that change to set everything back up to 0. So likewise, in this case where A minus 2B is equal to 0 or A is equal to 2B, actually I'll keep it like that. Minus 2B is equal to 0. A can change all it wants to, or B can change all it wants to, but the other one has to compensate for that change to keep this expression true. So for each of these equations here, we are gaining one additional quote-unquote degree of freedom. So we have 3 different one-dimensional lines, and as a result, each one of them contributes 1 degree, so we get 6 as our answer. And I actually really like how that works out, and you'll see that for these next 2 problems, we can use those, and this general strategy that works for Mn also works for Pn. So let's move on here to number 19. Let P4 be the space of all polynomials of degree at most 4. So let's draw out our generalized form of a polynomial in P4. It's some constant plus some constant times t plus some constant times t squared plus some constant times t cubed plus some constant times t to the 4th. And now we're told that we're dealing with the subspace V of all polynomials such that p at 0 is equal to 2p at 1. So p0 is just c0 because all of these other terms are multiplied by t, which is 0. And then 2p1 is 2c0 plus 2c1 plus 2c2 plus 2c3 plus 2c4. Now we can set these equal to each other, and we see that 0 must, we set these equal to each other, we get c0 on this side and 2c0 on that side. So we'll subtract that, and we'll just get that 0 is equal to c0 plus 2c1 plus 2c2 plus 2c3 plus 2c4. So, and this is a terrible 2. There we go. So just like in 3 dimensions, an equation with 3 variables equal to 0, so x plus y plus z equals 0, gives us, and because this is the first octant, this is going to be, I don't think I can draw that, but it gives us a plane, a 2-dimensional plane in 3 dimensions. What will happen when we have, what is this, 1, 2, 3, 4, 5 variables here? Well, just like how this 3-variable equation gave us a 2-dimensional plane, so we have 2 degrees of freedom in that plane. This not 5-dimensional, but 5-variable having equation will give us a dimension of 4, and that's it. So now this question is very, very similar. We're dealing in P3 this time, so P3 of t, the generalized polynomial in P3 is c0 plus c1t plus c2 t squared plus c3 t cubed, and we're told that p0 is equal to p1. p0 we know is just c0, and p1 is c0 plus c1 plus c2 plus c3. So this is where it can get you. They can really get you on this one, because we set these equal to each other. We can subtract a c0 from both sides, and we see that 0 is equal to c1 plus c2 plus c3. And I believe that my previous explanation for this question, I know for a fact, was, and I quote, there are 3 variables here, therefore it's a 3-dimensional subspace. But we know that a similar equation, x plus y plus z equals 0, well, that doesn't span R3. That's a plane, a 2-dimensional plane in R3. That it only has 2 dimensions. So you might look at this thing, knowing that, and say, okay, well, then this must be 2-dimensional. 2-dimensional. But what you'd be missing is that there's another variable that we're not seeing here, but just like in this example, how we had C, F, and I that we could move around all we wanted to, without changing any of these constraints, we have another purely free variable here. It's C0. Just because it's not involved in this equation down here doesn't mean that we don't have to take its degree of freedom into account. So in the end, we can vary C0 all we want, and then we can vary any two of these guys safely, as long as the third one picks up the slack to make sure that everything's still equal to 0. And as a result, we get 2 dimensions from this, 1 dimension from that, and we're left with 3. I really like how these end up working out, and I'm going to go relink my extremely bad explanation on the spreadsheet to this video. Okay, and finally, we are dealing with 3 different potential subspaces of P3. So, whenever you see multiplication like this, especially if we're squaring something, be very wary of that. I'll just put that out there, because that's not usually a good sign. But starting with number 1, let's see if we can prove some things. So we're dealing with polynomials in P3. Let's see, does this include the 0 polynomial? Well, does the 0 polynomial evaluated at 0 times the 0 polynomial evaluated at 2 equals 0? Well, that's just 0 times 0 equals 0. That's true. So this one includes the 0 polynomial. Is it closed under vector addition? Well, here's the kicker. Actually, we'll come right back to that. Is it closed under scalar multiplication? Yeah, because if this side evaluates to 0, then multiplying some constant by it, it'll still evaluate to 0. So it's closed under scalar multiplication. Check, check. What about vector addition? So it's very easy to craft 2 polynomials that work for this, add them together, and not see why it's not closed under vector addition. I'll show you why. Let's grab x, which evaluates to 0 at t at 0, and let's grab x times x minus 2, which evaluates to 0 at both of these guys. We add them together, and what happens? Well, when x is equal to 0, this thing will evaluate to 0, and when x is equal to 2, this will evaluate to 2. We multiply those together, we still get 0. So it looks good, right? But the thing is, and this is just some algebra that is very hard to come across your first time taking this exam, and I did not. I completely missed this. What you have to do is add 2 elements together, one of which evaluates to 0 for t at 0, and the other one evaluates to 0 for t equals 2. And when you do that, if we add these together, this is 2x minus 2 is equal to 0. What happens? Well, at x is equal to 0, we get negative 2, and when x is equal to 2, we get 2. So we can escape our set because this is not equal to 0 for vector addition, under vector addition. We're not closed under vector addition. And yet again, if you didn't find that on your first time through, that's completely normal. It would be extremely impressive, if you figured that one out. Maybe I'm just dumb. Okay, 2. The set of all polynomials in P3 such that p at 1 is equal to 4p at 0 plus 2. Okay, does this include the 0 polynomial? That's an interesting thing to try to think about, because if we evaluate the 0 polynomial at 1, we get 0. If we evaluate 4 times the 0 polynomial at 0, we get 0 plus 2. This is inconsistent. And so this is not closed under, well, it's not closed under having the 0 polynomial. I know that doesn't make sense. Okay. 3. The set of all polynomials in P3 such that p at 1 is equal to 0 and p at 4 is equal to 0. So let's just grab one. X minus 1 times x minus 4. It's good to note that the 0 polynomial does work here because the 0 polynomial at 1 is 0 and at 4 it is also 0. So 0 polynomial, we got that. What about scalar multiplication here? Well, if this guy is equal to 0, doesn't matter, just like up here, it doesn't matter what constant we multiply it by, it won't do anything to what this evaluating to 0 at its roots here. So scalar multiplication is a check. Now let's grab, well, actually we don't even have to grab another example. We can just think about it. If you have a polynomial that evaluates to 0, so let's see, we have polynomial 1. It evaluates to 0 at, so it has roots of 1 and 4. We have a polynomial, second polynomial with roots 1 and 4. What happens when you add them together? Well, you don't actually have to distribute anything. We can just say P1 plus P2. We know that when we plug in 1 to P1 and 1 to P2, we get 0. 0 plus 0 will still give us 0. And the same thing for 4. So we still get 0 for x is equal to 1 and 4. So vector addition is a check, and 3 is our only answer here. So surprisingly, this topic is actually pretty cool. Like when you figure out these dimension problems, like it's satisfying in a way that a lot of these other problems are not. So anyway, I think this is pretty cool, but maybe I just have Stockholm syndrome from so many subspaces. But either way, hopefully this was helpful if this was something that you needed review on.